Hello, today we are reviewing rational function graphs, and for us that's 2.6 day 1. So a whole lot of graphing, looking at all the parts of the graph as far as vertical asymptotes, horizontal asymptotes, holes, x-intercepts, y-intercepts, slant asymptotes or oblique asymptotes, roots, zeros, x-intercepts, and then being able to graph it as well. So we're going to work through some of these problems in this note set right here that you're looking at. We're not going to necessarily do all of them because some of them are interesting graphs, and I want you to be exposed to some interesting graphs, but I would not necessarily give you anything that difficult to do on the test. So the first thing that I want to talk about is the parent functions that you learned in Algebra 2. We studied two rational parent functions. One is rational odd, which is f of x equals 1 over x, and one is rational even, which is f of x equals 1 over x squared. The rational odd parent function has branches in the first and third quadrant. The parent function points that we used were 1, 1 for the branch in the first quadrant and negative 1, negative 1 for the branch in the second quadrant. It has vertical asymptote at x equals 0, and we have a horizontal asymptote at y equals 0. The domain would be all real numbers except 0, because remember you're doing domain left to right, so you're reading across the graph that way, and you would have to skip the vertical asymptote. Range would go bottom to top, so I would say from negative infinity to 0, skip over 0, and head out to positive infinity. The end behavior as you're running down the graph here and going out to positive infinity, so as x goes to positive infinity, f of x is going to approach 0, that horizontal asymptote. When you go the other direction, if you come up the graph and head out here, as x goes to negative infinity, the y value is also approaching 0, and that's the horizontal asymptote. On rational even, 1 over x squared, notice that the second branch now is up here in quadrant 2, which should make good sense because there's not a number that I could ever put in here that's going to give me a negative answer. Therefore, there shouldn't be any graph down here where the negative y's are, which would be where your negative answers would be. So the parent function points on rational even are 1, 1 and negative 1, 1. And so that's a little different there. The end behavior as x approaches infinity, f of x approaches 0. And when you go this way, as x approaches negative infinity, f of x approaches 0 as well. The domain for the rational even would be the same. You're reading the graph left to right, so you're going to have to skip the vertical asymptote. So we go from negative infinity to 0, parenthesis, union symbol, parenthesis, 0 to infinity. If you're going for the range, notice it goes up here and it starts right there on the horizontal asymptote. However, it is horizontal asymptote, so you wouldn't include it. So you would say parentheses and start at 0 and go to infinity. So when you're doing rational graphing, there are a lot of things that you consider. So here is an example, and I'm showing you all of the different things that I would have needed to determine before I can actually get to the graph. I always got students that say that they aren't any good at rational graphing because when they look at it, they don't know what the graph looks like. And that's kind of silly because look at all of this stuff that goes into the graph. No one is going to just instantaneously know that in their head. You have to stop, take a look at all of the pieces. Once you get the pieces, in and of themselves, they're pretty easy. And then you put all of those pieces together, and then you'll finally be able to see and look at the graph. So even I, after as long as I've been doing these kind of problems, wouldn't have known exactly what this looks like as a graph without first looking at these pieces. So what I'd like for you to get in the habit of thinking is, okay, here's what I'm going to graph. Now I'm going to find all the stuff I need. Then I'll worry about the graph at the end, and not the other way around. I think that sometimes you set yourself up to struggle when you do that, and all of the pieces in and of themselves, none of them are very difficult. So if you can just get the little pieces down, you are going to be good to go for me. As I was saying, there are a lot of pieces to a rational graph, and this is a possible graphing order. I say a possible one because it's not the end-all be-all. You can do things in lots of different ways. I will give you some pointers as to how I think would be easier, maybe sometimes to do certain things than others, but this is just a suggestion. In the end, you're going to look at all of this stuff and figure out all of these pieces, and then you would go to the graph at the end. So we're going to find horizontal asymptotes. We're going to do factor cancel to find common factors. When we do a factor cancel, then we're going to determine if there are any holes. Then we're going to look for like y-intercepts, vertical asymptotes. We're going to introduce today slant asymptotes or oblique asymptotes. We'll look at roots, zeros, and x-intercepts. We're going to look to see if the function crosses the horizontal asymptote. And then finally, after all of that, then we would graph and verify our graph with a plus-minus number line. So remember, on a plus-minus number line, we're going to put vertical asymptotes and zeros. And so when you're doing a plus-minus number line, you're going to have not include the number that's the vertical asymptote, but include the zeros of the function. So the first thing we're going to do is review some end behavior, which has to do with our horizontal asymptotes. Remember that we study horizontal asymptotes. We're talking about long-term end behavior. So way, way out to the left, what's going on? Way, way out to the right, what's going on? We can sometimes cross a horizontal asymptote because it might kind of pass across the horizontal asymptote and then finally level off toward the horizontal asymptote when you get way, way out there. So I always ask students, do you know what Bobo, Bot, and Betsy is? And then about most of my students say, well, we learned it, but we don't know what to use it for. That tells me that you didn't learn the why. If you understand why it works, then the memory device is helpful. But if you don't understand what's going on, then it can be a bit of a challenge. So what the behaviors here are doing is determining in behavior, determining what's going on out there. And we're using the horizontal asymptote to help us do that. So if you're looking at a polynomial, you're going to remember the definition of a rational function is the division of two polynomials. So I have a polynomial on top and a polynomial on bottom. I'm going to look at the degreed term, meaning the highest power of x on the top and the highest power of x on the bottom. And I'm just going to pull it off for the sake of these problems. So for instance, when I'm looking at this problem, there could be like 2x to the fourth plus 3x cubed plus 2x squared plus 5 on top and 3x plus 4 on bottom. So what I did is I pulled out the highest power of x on top, the highest power of x on bottom. Now, once I've done that, I'm looking at what's going on with this particular problem. So I can see that the top is taking a number that we put in for x and raising it to the power of 4. So this number is going to grow pretty big pretty fast, and each time I'm multiplying it by 2. Well, down here on the bottom, I have a linear function. Well, the linear is still increasing, but it's not increasing near as fast as what you see on the top. So this number on the top is kind of taking precedent and it's pulling it out toward infinity, which means behavior is not going to go to a specific number. And so this particular case would be what we would call a bottom. And the reason is the x to the fourth is growing faster than the x. And so when that happens, there is no HA. In other words, no horizontal asymptotes. And that's what we call a bottom. The abbreviation bottom stands for bigger on top. So it's talking about the degree. So the degree is bigger on the top than it is the bottom. And when that happens, there is no horizontal asymptote. And that could sometimes mean that maybe you have a function that simplifies to behave like another function. So maybe we have like this rational that's simplifying to behave like a linear function, or this polynomial that's simplifying to behave like a quadratic. In which case, they don't have asymptotes, so there would be none. Sometimes it will simplify to where it will develop a slant asymptote, and we'll talk more about that later. But that's just one of the possibilities. So that's what a bottom would look like. Okay, so now we're going to look at this one. So we have f of x equals x over 2x to the fourth. So I'm thinking about what's going on here, and I'm looking at this, and I'm thinking, okay, I got a linear function on the top, but now I've got that on the bottom. And so as these x numbers get bigger and bigger and bigger, the value of the function, the value of that fraction is getting smaller. Think about this if this were a number, and let's say x was 1. But I simplified all this and I ended up with the fraction 1/2. Okay, if the fraction then becomes 1/4, well, think in terms of decimals, if you will. 1/4 is 0.25. 1/2 was 5. So even though the number on bottom was bigger, the value of the fraction got smaller. And let's say then, what if it was 1/5 or 1/6 or 1/7? So as these numbers on the bottom are getting bigger, the value of the fraction is getting smaller and smaller and smaller. So as the x to the fourth grows faster than the x, the value of the function gets smaller, and we have a horizontal asymptote at 0. And that's what we call our BOBO. BOBO stands for the degree is bigger on the bottom, so it's going to happen at 0. And so be sure you write your equation as an equation. If you put HA equals 0, I'm sorry I can't give you credit for that, because that doesn't tell me if your line's going vertical or horizontal. If you just put a 0, then you haven't given me the equation of a line. So really be careful here and make sure it's y equals 0. So on this particular problem, now we can see that the top and the bottom aren't growing at different rates, right? This isn't bigger than this isn't bigger than that. So that means that x squared is growing at the same rate as the bottom. And what happens here is then you kind of get a value that converges or hovers around a specific number. And the number is the ratio of these coefficients. Think about this as an algebra problem. If we were simplifying an algebra problem, we would take and simplify any common factors. So I could mark out an x squared on both of them because anything divided by itself is 1. And I would be left with this fraction 3/5. Well, being left with that fraction of 3/5 is also being left with the horizontal asymptote. The horizontal asymptote is going to be at 3/5. And remember again, it's y equals 3/5. And this would be what we call a Betsy, which is bottom equals top. It's at the coefficients. So you just take the coefficients of this when it's a Betsy. Okay. So the last one, take a moment, look at this. And we're thinking, okay, x squared on top, x on bottom. I can take 1x out here. I can take 1x out here. So now I have 6x on top. And I know 3 divides into 6 2 times. So now I have 2x on top. And that's bigger on the top than the bottom. So I have no ha again. And that is Bobo, Botan, Betsy. In this case, it would be a Botan. So now let's talk about slant asymptotes. These are new. You did not study these in Algebra 2, so we are adding one new thing to our graphing, and sometimes they're called oblique asymptotes. I tend to call them slant asymptotes. Either one is perfectly fine. Slant asymptotes occur after the factor cancel process has happened, and we're left with the degree of the top being exactly one more than the degree on the bottom. When that's the case, then a slant asymptote is going to arise. So think about this for just a second. When we have a vertical asymptote, it's a vertical line. When we have a horizontal asymptote, it's a horizontal line. When we have a slant asymptote, well, that's just a line. So it's going to look like the equation of a linear function. It's going to be a line. So let's take a moment and kind of look through a problem. So if I have this problem, then I am going to look at it, see if it factors, and I always write that down. Then I would look at it and see, okay, there's nothing that's going to cancel, but I have a degree of 2 on top and a degree of 1 on bottom. Since the top is exactly 1 degree more than the bottom, then I know I have a slant asymptote. When I have a slant asymptote, and I know I have a slant asymptote, then I'm going to have to use my division to find it. So because this is linear on the bottom, I could do synthetic division, which gives me this quotient. Or I could do long division, which again gives me this quotient. Now what we did is we took this function and we wrote it as a quotient. Well, if you think about what's going on here with the remainder, as x gets bigger, again the value of the fraction is getting smaller, and eventually this would go to 0. So since it's going to 0, I really don't have to worry too much about that, but right here is where I would find the equation to my slant asymptote. So I would say the slant asymptote is that y equals -2. Now if it is anything but linear, then you would have to use synthetic division, but I personally like it when I can use synthetic division. It does make it a little quicker. Now let the fun begin. So now we're going to do what I talked about. We're going to find all the pieces. We're going to worry about the graph at the end. So as I go through it, I would say, does it have a ha? No. The degree is bigger on the top, so there's no ha. Then I might do factor cancel. Well, I looked at factor cancel, but there really was nothing to cancel, so no hole. Then I'm going to check to see if it crosses the horizontal asymptote. Well, if there's no horizontal asymptote, there's nothing there for it to cross, so that's an easy no. Then I would look for the vertical asymptotes and the roots. So remember that when you simplify a fraction, anywhere in the denominator left where x can turn to 0 is where you would find a vertical asymptote, and anywhere left in the numerator where it could turn to 0 would be where you're going to find the zeros of the function. So on the bottom, x minus 1 would make that 0, so the vertical asymptote is at x equals -1. Remember that equation. The roots are going to happen from the top, so I can see I have a 0 right here at x and a 0 here at +1, so I'm going to write those down. I'm going to get my slant asymptote by doing this division and only looking at the quotient part, so I'm going to write that down. To get my y-intercept, I'm going to plug in 0 into the equation, so 0 minus 0 gives me a 0 on top, so I know that's at the coordinate point 0, 0. Remember, x-intercepts and coordinate points need to be written as, x-intercepts and y-intercepts need to be written in coordinate pair form. So then I would actually put my stuff on the graph. So I know I have a vertical asymptote at -1, so I probably would put an open circle there just to make sure I didn't actually include it, because it is a vertical asymptote after all. And the zeros came from 0 and 1, so I would put solid dots. That's something is a little different from the plus minus number lines we did before, because we didn't have situations like this where it's not included. So once I have that, then I test values in each area, and I can tell it's going to be minus, plus, minus, plus. So now let's actually put it to graph. So I'm doing all of this before I go to the graph. Now I'll worry about the graph. So I usually draw my asymptotes first. So I do my vertical one at -1. I plotted this line, so I went down here to -2 and put a point, and then I went up 1 over 1, up 1 over 1, and I was able to graph the slant asymptote, and notice it's a slanted line. All right, so once I do that, then I put my points on, so I had my zeros right here, and so I can tell, remember that when we put the vertical asymptote right there, it splits the graph into this half and this half. And so I need to figure out where the graph is on this half by finding points on the branches. If I already have roots or y-intercepts or holes, I can use those as anchors to my graph. If not, then I have to calculate one. And so on this side, I already had 2 zeros, so I got close to the asymptote, went through the zeros, and got close to the asymptote on that side, and that's my rough sketch of that branch. But now I'm on this side, and I had nothing from this list to be able to put on there, so I had to calculate. So I went to a number just on this side of the vertical asymptote, which is -2, and then I put it back in here in the problem. So I said -2 squared is +4, minus a -2, and I calculated all of that. And so that gave me that 6. So that was the point I used, -2, 6. And once I have that, now I know this branch is trapped between the slant asymptote and the vertical asymptote. So it gets close to the asymptote, goes through the point, and comes back out close to the asymptote on this side. So that's really all there is to graphing. If you notice, none of these little things in and of itself in any little piece was challenging or difficult. So don't think you can go immediately to the graph. Do the work, build the points, build the process, and then you'll be easy peasy getting the graphs on there. So let's take a look at number 2, problem 1, or number 2A. So here's my function. There's nothing there to factor cancel. I would typically say the first thing I do is the horizontal asymptote, because that's when you're going to want that unfactored form. It's easier. So unfortunately this isn't that way. So I would multiply x times x and get x squared. So I know it's bigger on the bottom, so the horizontal asymptote is at y equals 0. Well, I know that if there's a horizontal asymptote, then there can't be a slant one. So I'm going to go ahead and write that one down, so I know that's out of the way. And then I would factor and cancel. Well, it doesn't factor and it doesn't cancel. There's no factors there. The reason I do that at this point is to get a whole, you have to have something that cancels out. If there's nothing that cancels out, then you have no whole. So I can say now I know for sure there are no holes because nothing canceled out. So remember then in the denominator right here, whatever will make this equal to 0 is the vertical asymptote, and that's going to be at +2. So I write the equation y equals +2. Then I look in the top, and there are no degrees up there, or if you want to think of it as x to the 0 power, you could. but there's no x's in there to plug into, so there is no zeros. Does it cross the HA? Well, to do that, I set up a proportion. So my horizontal asymptote is 0, so I would say 0 over 1, because you can make any fraction or any whole number into a fraction by putting it over 1. And then I would set it equal to this. And when I solve that, then I get 2 equals 0, which can't happen, so now I know it doesn't cross. All right, so here's what I was talking about. I put my horizontal asymptote over 1. I put the simplified version over here, and then I said this times this, and this times this, and then I solved and found that 2 does not equal 0. So now I know it doesn't cross. The y-intercept is what I get when I plug 0 in for x, so when I plug a 0 in there, I get negative 2 squared, which is 4. 2/4 simplifies to 1/2, and I write that as a coordinate point. Okay, so then when I'm doing my number line, I have the vertical asymptote, which is at 2, and so not a part of the graph. And then I tested the points on each side. And so when I tested this side, I got a positive. When I tested this side, I got a positive. And that mirrors what's going on here. So I have my asymptotes and look at the branch staying on this side and the branch staying on that side. Problem B is right here, and that is x squared over x squared minus 1. So the bottom is going to factor, but nothing's going to cancel. The horizontal asymptote is at y equals 1 because the numerator is 2. The power of the numerator is 2. The power of the denominator is 2. And so these would cancel out, and you'd be left with the coefficients that are in front of their numbers, which are 1. If there's a horizontal asymptote, we have no slant asymptote. So then I would probably factor and cancel, which I've already looked at the factorization. There are no holes because nothing canceled. The stuff left in the denominator is where you get your vertical asymptotes, so that's going to happen at positive 1 and negative 1. And the stuff in top is where you get your zeros, roots, or x-intercepts. And in this case, that's going to be 0. So notice that I wrote the vertical asymptotes as 2 equations. I wrote the 0 as an equation. Does it cross the horizontal asymptote? Well, we take the simplified version equals, and then we take 1 over 1 because that's how you would set up that fraction. Then you multiply. So this times this equals this times this, and you get 0 equals negative 1. Problem C is just one of those I put on here for fun so you could see an interesting graph, because look how crazy that graph looks. But eventually it's settling out just underneath the horizontal asymptote, whereas on this side it's settling out just above the horizontal asymptote. But I wanted to point this out because it was quadratic, and the only way that you could tell is if you're looking to do the quadratic formula when it doesn't factor. And if that's the case, remember the discriminant is the number under the radical. You can calculate just that piece right there. If that's negative, then you know it's imaginary and it's not going to have x-intercepts. We can determine that the HA is at 2 because these are the same. So the ratio would be of the coefficients is 2 over 1, which is 2, and we write it as an equation. If we have a SAW, we don't, or if we have a horizontal asymptote, we don't have a SAW. So that's just kind of one so you could see a nice interesting graph. Before we go any further, I just want to review form. So I'm treating A like a number. So if x equals a number, then you can write that as a 0. X equals number, that's a solution. X minus A, that's a factor. So we have to be careful when it asks for factors or solutions, because I still have people that are confusing the two. And then if it asks for an x-intercept, it's going to be that number, comma 0, and it must be in coordinate point form. If you're doing, generally speaking, the domain, remember you go left to right, so you're going to have to exclude the vertical asymptotes and the x values of the whole. And then if the range goes bottom to top, you're going to exclude the horizontal asymptotes and the y values of the whole. And then do be mindful about when we talked about if there's a gap in the graph, because you don't know how to make those calculations yet. So you may just have to describe it. You may say something like, you know, all real numbers, but y can't be the values between branches, something like that. And then when we do the number line on rationals, please remember it's zeros and vertical asymptotes, so make some way to denote that on your plus or minus number line. Some people draw a little vertical asymptote there. Some people do the zeros like I was doing. So either one's fine. Remember that you need to assign a plus or minus for each part, and when you're through with that plus or minus number line, it should mirror what's happening on your graph. All right, on number 3A, here is my function. Nothing is going to factor and cancel. The horizontal asymptote, the power on top is 2, the power on bottom is 1. It's bigger on the top, so there is no horizontal asymptote. There is a slant asymptote, however, because the degree on top is exactly 1 bigger than the degree on bottom. So since this is linear, I'm going to use my synthetic division, putting a 1 for the x squared term, a 0 for the x because that's missing, and then a negative 1 as your constant. Perform the operation. Don't worry about the remainder, and your slant asymptote equation is going to come from this right here, which is going to make it y equals x minus 1. Again, all asymptotes have to be written as an equation. All right, so we factored here and nothing to cancel. So there is no holes. Now I'm going to check to see if there's a vertical asymptote. So I'm looking at this bottom part right here, the bottom part. That's where your vertical asymptotes are. And you are going to set that equal to 0. So the vertical asymptote is going to be at x equals negative 2. Then we'll look to the top. So when we look to the top, I can have a 0 right here at a positive 1 and a 0 here at negative 1. So I have these two zeros. I get my y-intercept by plugging in a 0, and you can either plug it in here or plug it in up there, and that gave me negative 1/2. Does it cross the horizontal asymptote? Nope, it can't because there's not one to cross. And then we have our domain, which is going to be all real numbers, where x is not equal to negative 2. The range is going to be a little bit different because we have this skip and graph right here. So when I'm writing the range, I'm going to say and use my all real number symbol. And then I don't really have any holes or anything to skip. So I'm going to say the y's can't equal the values between branches. And we just have to describe it like that because I don't know how to make this calculation yet. And you can see a whole lot of points there that would not be included. So then we go over to our graph. We have our vertical asymptote. We have our slant asymptote. We have our zeros right here. We have this branch down here. And I got that by calculating a value. So I calculated my negative 3, and that put it down here on the graph. Sorry, I didn't label that. So we'd be looking at the point negative 3, negative 8. And that's the point I would use to anchor the branch. So down here, it's trapped between the slant asymptote and the vertical asymptote. 3B is another one of those graphs I just put on here so you could see some interesting graphs. Notice that the difference of cubes is not going to go away. Notice the sum of cubes is not going to go away. Notice this is an x squared down here, and it's exactly one number bigger on the top than the bottom. So I'm going to have a slant asymptote. And when I have a slant asymptote, I need to use division, and I'm not able to use synthetic division because this is a power of 2. So I actually had to do the division to get the equation of the slant asymptote. And so then we can go through the other process, but you can see we had a really interesting graph here. I would not give you one that difficult on an assessment. All right, problem 3C, x plus 2 over x plus 3. Obviously, there's nothing to factor cancel there. The degree on top is the same as the degree on bottom, so its horizontal asymptote is at the ratio. So the horizontal asymptote is going to be y equals 1. There is no slant asymptote because the top is not bigger than the bottom. So we can move on. It's not factorable. The holes, nothing cancels, so there are no holes. What's left in the bottom turns to 0 when x is negative 3, so my vertical asymptote is x equals negative 3. What's left on top turns to 0 when x is negative 2, so zeros I'm going to write as x equals negative 2. To calculate the y-intercept, I plug a 0 in here and a 0 in here. That leaves me with a y-intercept of 2, 3, and don't forget the x-coordinate is 0. And then I want to see, does it cross the HA? Well, my horizontal asymptote is 1, so I write that down, and I divide by 1 because I can make that into a fraction. And then it's equal to the simplified number, which is right here. So then when I solve like a proportion, I would do x plus 3 times 1 and 1 times x plus 2, and I get this statement. And look what's going on. I have an x and an x, one on each side of the equal sign with the exact same sign, And so those are going to eliminate each other, because if I move this one over here, now these are going to produce a 0. And if I move this x over here, now these are going to produce a 0. So I know I can get rid of the x's, and I'm left with 2/3. And we know 2 can't ever equal 3 because those are different numbers. So then I know it's not going to cross the HA. So then when I go to my number line, remember the vertical asymptote was right here, so I'm going to put an open circle. And then -2 was a 0, so I'm going to put a solid circle there so I can remember how that's going to play out and mirror my number. So then I put everything on the graph. So I have a vertical asymptote, a horizontal asymptote, I have a y-intercept, I have a 0. So I had everything I needed from all our information to graph this side. So it's going to come from here, it's going to go through that point, it's going to hit the y-intercept and head on out close to that asymptote because we know it's not going to cross the horizontal. And then on the other side I needed to calculate a value, so I calculated -4 and I got a y value of 2, so that put that branch right here, and so I get close to the asymptote, goes through that point and out the other side. And so that's what the graph on 3C would look like. The last one we're going to look at is 4C. So in this case, I have a polynomial on top and a polynomial on bottom. So I'm going to look here at the degree term on top and bottom. So this is a power 3, this is a power 2. So it's bigger on top than the bottom, so I know there's not going to be horizontal asymptote. So then I'm going to factor the top, and that factors down to x times x plus 4 times x plus 2. And I'll factor the bottom, which is going to factor to x plus 4, x plus 3. So then I can get rid of my common factor, which is x plus 4. So that's where the hole is going to be. I'm going to have vertical asymptotes where the x on the bottom is left. I'm going to have roots or zeros where the x's on top are left. So that's where I write down my simplified form. So once I get the simplified form, this is what I'm going to use to do the division with, because it's a whole lot easier to do synthetic with this form than it would be to do long division with this form. So I put my -3 from the bottom. I have x squared plus 2x on top. So there's a coefficient of 1, there's a coefficient of 2, and there is 0. So I do my division and I get x minus 1. Okay, so once we have the slant equation of the asymptote, it's at y equals x minus 1. You've done your division. So now we've got to figure out if it's going to cross the HA. Well, if I look up here and there's no HA, then there is no HA to cross, so that's an easy one to mark off the list. So now we need to figure out the hole. So the hole is going to occur where things cancel. So if I'm looking right here, I can see that x plus 4 is going to cancel with x plus 4. That's where a hole is going to happen at. So when I look at this one, where is x plus 4 going to be 0 when x equals -4? And that's what becomes the x value of the hole. Now remember, you learned in Algebra 2, when you factor cancel, you get this simplified version. So here, we still have the hole, it's right there. But once we remove the point of discontinuity, the hole no longer exists in this part of the function. So when you're right here, there is no hole, and I can plug that -4 back in right here and actually be able to calculate a y value. If you try to plug it back into this equation, the hole is still there, so it's not going to let you come up with an answer for y. So you always have to remember to plug it into the simplified version, the version where we have removed the point of discontinuity. So then our VA is right here, so we know when that turns to 0 is -3, and we write it as an equation. And then the roots or zeros are on the top, and we set that equal to 0. So x equals 0 here, and when x is -2, this factor equals 0 there. So I have two possibilities. So notice roots or solutions or zeros will be written in this format, and then x-intercepts would be written as a coordinate point. So then I'm going to go ahead and figure my y real quick. If I put a 0 in here for all of these x's, then I know that my y-intercept is at 0, 0. So that's my coordinate point. So all of these things. So I'm going to skip over domain and range for a minute. I'm not sure how I ended up writing that in the middle of the problem and the y-intercept down here, but I did. And then we're going to start putting everything on the graph. So I'm going to put the vertical asymptote here. I'm going to do the slant asymptote, which remember the equation is y equals x minus 1. So I come down here to -1, and the slope is +1 right there. So I go up 1 over 1, up 1 over 1, and then I get my slanted asymptote, my oblique slant asymptote right there. I plot the zeros, which are at -2 and 0 here, and that also happens to be the y-intercept. And then I have a hole. So I go over here to -4, I go down to 8, and I draw an open circle because the hole isn't included. So really this works out well because here's my vertical asymptote, and you can see I have these 2 points right here, so I can sketch in my graph close to the asymptote through the zeros, back out close to the asymptote. And then on this side I have a hole down here to anchor it with, so I can go asymptote to the hole and come out this side. Be really careful when you're drawing on a hole and that you don't accidentally fill it in when you draw over it, because if it's filled in, it's no longer a hole, and that would be an incorrect point on the graph. So then remember, when we look at our plus and minus number line, I have a vertical asymptote here, so that's an open circle. I have zeros here and here. So then on my number line, when I calculated, I got minus, plus, minus, plus. So notice everything to the left of -3 is down here below, which also gives me a little hint telling me that this branch couldn't have been up here, because if the branch was up here, it would be below and above, right? So that tells me that. And then from -3 to -2, it's positive right here in the graph. And then from -2 to 0, it's negative, so it's below right there. And then from 0 on, it's all the way positive up there. And so you can see all of that. So it's easy to tell your domain, because remember, your domain goes left to right. So I'm traveling this way. I'm skipping over the x value of the hole. I'm skipping over the vertical asymptote, and I'm going on out that way. So I have the domain is all real numbers, but x can't be -4 or -3. It's way easier to use this notation than to try and use the interval notation, because you're skipping your u's and stuff. And then the range goes bottom to top, so you're coming up to here and skipping that hole. So I need the y value of the hole, which was at -8. And then I've got to recognize in my range that I'm missing these values. I just don't know how to calculate those values yet, because you need different skills to do that. So this is the way I would write it. All real numbers, the y can't be -8, or the y values between the branches. So it's going to look a little different. It's not going to be solely in notation right now, because you need a little more information to be able to do that. So that's everything when it comes to a rational graph, and this number 4 I think pretty much had most everything on it. So I'm hoping that you get now, after we worked through these problems together and talked about them, that it's not about being able to look at this and instantaneously know how to graph it, because it's not a transformation problem. But if we take this and break it into all these little pieces, then no one piece is going to keep us from being able to get to a graph. So I think the hardest thing is just kind of getting in your mindset how you want to do it. But if you notice, several of these problems that I didn't do it the exact same way each time, right? The order changed up depending on what was in the problem and what I saw. All right, guys, thanks so much. Bye.